Okay, we'll get started. Let's see. So let me move things around first. This is something else. That is something else as well. Okay. So I guess what I'm going to do, let me pull out that. Yeah, I need to make sure I didn't pull out the solution of last homework. I'm preparing to of a last homework. The last homework. Let's see. I want to. Last time we talked kind of like talk more about optical flow, and then like we ended like with some illustration, right? So I guess I will just continue on that one first. Yeah, I didn't share screen yet. So here's what I have. So to make sure I didn't have anything funny like on my screen. So anyway, so this is basic. Okay, I'm not sure. Yeah, it's okay. I show you the code. So we talk about several optical flow. Maybe I put up one of this thing, just remind you guys that what we have there is like the main thing is like we have this brightness constancy equations that so we assume like for the previous frame, like we warp this current frame, like, or like each pixel move a little bit by time u x y and v x y, and so the next frame that brightness for the intensity for that after the shift should be equal to the current frame right now. So and based on that, we derive like several optical flow method. So one of them is like this Lucas candidate that I am showing here. So for the yeah, I guess I should. So for Lucas candidate, so the implementation there, okay, like in OpenCV, it's actually a so-called like not a sparse like yeah, of course like for everything we talk about like there we assume like kind of like dense implementation for each of the XY. We're going to compute the flow there, right? For each of the UX, for each XY we compute the flow UXY and VXY. But for Lucas candidate here, so it's assuming that you are doing a sparse kind of flow computation. So we specify like some point like good to track. This is just some corner points. So here you look at the future parameters put into that. It's like basically parameter like for like the Sutomashi corner detector. That's basically like if you will remember, it's a variation of Harris corner detector. And so actually, I guess I showed that to you before, like that's when I run that. So it's like kind of like only have like a couple points you're trying to track, and then you just track those points using optical flow, basically. So the remaining code is just the illustrate the visualization, trying to visualize the points that the optical flow Lucas candidate is tracking. And let's look at a slight variation that okay, what's this? Let me see. Okay, and maybe I should okay, yeah, this maybe this one. Um I guess I want to run this one first. I see. So this is like the same code, but like I'm playing with a live demo on not a pre-recorded video, but like just on my laptop and so on. So the dots here, like what I'm going to show you is like how it tracks the dots. Like in the sense, like for example, like this dot here. Okay, maybe I play around this dot here. Yeah, move around. Let's see if I can move it around. So what I want to point out is like you see, like it cannot track horizontally. Like if I move like this, it won't be able to track it because it's the same problem. Like if you remember, like we with that matrix M, that basically like the cornerless of like some pixel there. Like when it's like edge like, yeah, okay, we don't need to go to the map, but like when it's edge like apparently like it cannot specify, it cannot really realize whether it's like it's it's I mean that it's not there's no distinct feature for it to track. But if I go to corner, then maybe I can move it. Yeah, maybe it's still not. Yeah, I don't know. Let's try another pawn here. Maybe this blue one. Maybe I try some other thing too. How about this green one here? Or they are very stubborn like, on that place here. So maybe how about I try this one here? Huh. So anyway, it's doing something, but I'm just saying that like, it's not super accurate. So we will talk about tracking more. Like just focus on tracking today. Actually, we will focus on just one algorithm, like the KLT tracker. That's basically an extension of the Lucas kind algorithm. And let's look at another illustration here. Okay, this one, ignore this one. Let's see this one. Like, so it's another optical flow, but I'm using like funnel, what's that called? Like kind of funnel back instead. And so, and this is like the implementation is a dense flow algorithm. So it's not very clear. So what's going on is like, again, it's my camera, I put a hand in front of that. So if I move it, it kind of able to track the motion there. Yeah. So, and maybe, okay, another illustration may be better. Like, let's look at this one here. So here I'm just using Ghana back again, but I am visualizing like kind of like the plotting the vector instead. So again, like if I have like some object, like if like I'm on the edge somewhere, if my motion is like is kind of like parallel to the edge, then it won't be able to track the motion right there. Is as you expected. For example, I put my palm here. If I move back and forth, if you see like here in the middle here, it okay. Apparently, I have my laptop hangs. Just wait a sec. So I need to wait a little bit time here, like just to have my laptop reboot. Um, Okay, I'm almost get myself back. I'm back. So hopefully, uh, yeah, hopefully it won't have like. Still, the fan is running pretty high. I don't know why. So okay, let me share my screen again. Let me pull out the. Okay, so so as I said, like we are going to talk about tracking today. So and see. Go forward. Okay. I think like do I need to activate something? Yeah, some video here. I'm not sure it will run because I haven't. Oh yeah, it's okay. So um, so we're going to talk about tracking. More precisely, we will talk about like KLT tracking, KLT tracker, Carter, Lucas, Tomashi tracker. And but to start with, let's have an overview of tracking first. So of course, the tracking is very intuitive. Right? You have some objects you want to track on the in your video and so on. So and I will skip this. I just this is an illustration. This is of course is a very simple case because you have the car. It doesn't change the shape and size or anything. Like it's almost identical. You can use a simple like template tracking like will do really well for this one. And this is another example like multi-object tracking. So multi-object tracking is much more challenging. In particular, in this case, you have the pedestrian have they change the gesture, I should say the pose. So therefore, like it's not something rigid that you can use a template and keep track of like for previous frame. And in general, it's still a I won't consider it's a completely solved problem because um, if you look at the state of the art algorithm, they still won't give you 100% like tracking results. Like, it won't be as good as, like, for example, a human. If you're a human trying to track the scene, of course, like for human, you cannot do the same thing, like track everyone at the same time. But we do a pretty good job. Like for example, if we track one person here, maybe this 20th, you see like they this one, of course, like this is not the state of the art, but you see the result is not robust. Like for example, this 9 here. Okay, yeah, maybe I should start with like you see this 23 here. Let's see.
I have a question.
Yes.
So we see that it like pops up from like the numbered from what they see first, basically. Is there a way that you could take those numbers and store it Or is it like as soon as, let's say, 2 goes out of frame, does someone else replace the 2, or is he always assigned to 2 now?
No, it's not. Yeah, it's something like it's just a simple ID here. So it's like a counter. Like I guess in this case, in this example here, the ID is just increment like by 1 every time you have a new subject coming in. You just add a new ID to him. But I maybe it's not clear for some of this. Like sometimes it lose track. And then like you will assign a new ID for someone. For example, let's see if it happened. Yeah. I mean, supposedly like you should have only a new subject like coming in from the boundary, right, of the video here, but you may have like new subjects just coming in anytime, because like, it just failed to kind of like detect it at the beginning. I'm not sure I answer your question really, but that ID is not really something. I mean, for example, maybe like take another example, like maybe this one here. So if you have multiple camera, ideally you want to have, for example, like someone's coming in like in one camera, uh, then if this is the same person, you will have the same ID applied to that same person. So it depends on your algorithm. Like for these cases, you're doing both tracking, detection, and also recognition, right? So you want to re-identify that person there. Um, but for this example here, that definitely is not doing re-identification. So it's not something like doing recognition real time here. I think like it just do the pedestrian detection afterward, like it keep track it like with a temporary ID. So is that clear?
Yeah, that makes sense. Yeah.
Yeah. So and this is another example. So this is also an example like with a fixed camera. If your camera is not moving, then it's like the problem is much easier. So if, for example, if I have this, the camera is also moving, and this one, this person like doing this flip here, have like loss of motion, it's make the problem is much more challenging actually. And yeah, we see that before. And so just mention some of these challenges. Like very obvious one, like you have the subject like can be not rigid. For example, if you have a car, then it will be easier to check. But if you're a pedestrian, like you have say lots of different motion poses, then that's much harder to check. And you have like other challenges such as like occlusion. Like I don't think I put occlusion here somewhere. So like that subject may move into a shadow like or behind a tree and then come back out again. So you need to be able to kind of take care of these kind of situations. Um, in general, it's not okay. Occlusion is here. So and also like if you have error, like if you use like for example a template matching, if you don't vary the template, then the error will accumulate, right? So because when it first cut into the scene, like it looks like this, but after a while, like it changes, right? So and also like okay, what good feature to track? Or like of course, like what we're interested in, like we are this is saying that what is good to track, but the question should be like we have this person, we are interested to track that person, right? But in that person, maybe there's some features it's better to track. And all these things is apparent if you, I don't know, like at least like for if you want to offer like some simple, not very complicated solution, maybe like some of you guys want to explore like let's say deep learning stuff, like I see like in some of your projects, but like in some classic more simple like algorithm, like it just goes down again. Like if the features it's similar to like SIF when we talk about Harris corner detector, it's always like if there's more texture, more high frequency component, it will be easier to check. Um, and yeah, that's just repeating what I said. So and some apparent technique, as we mentioned already, like we can use optical flow. So we have just have that example like in Lucas Canada. So if we have some points like in the car, we think there's some points that is good to track. We just keep checking those points. Yeah, we can kind of have a checking algorithm like that. And we can like check other features as well. Like the simplest one would be like just taking the entire image, or like you just entire region of interest as a template and try to track that template. Or like you can kind of transform into some other domain, like maybe do some wavelet transform, or we didn't go into that like here, but we'll see like when we talk about later here, like to talk about like Lucas Calendar, sorry, like the KLT tracker. Then essentially it's also like we actually I shouldn't say that, but we will go into that. So that's just a okay. This is another nice illustration that an application of using this KLT tracker. So you can check the scene here, for example, like using the scene to get the orientation of your, maybe your this is a robot or something, and so can do the slam for that. Okay, so he is showing that okay, it's simultaneously localize itself and also like creating a map. And this is the illustration of KLT tracker, so that we are going to talk about today. And that's this one. That's it one. Oh yeah, it's just as again another illustration checking simply checking a car, checking cars. And this is a interesting illustration that is checking like not just the motion but trying to compute the normal. Have some 3D information here. But we are not going to that here like today at least. So that's basically I guess all my slides like this. So I will go into some. Let me. I hope it didn't crash again. Okay. Okay, we have this earlier. Let me also show my slides. Maybe I'll move this down here. Then I move up here. Okay, so let me get. Oh, okay. Where's my pen? Ah, that's bad. Okay, finally. So, but I need to. Oops, I forgot to, because I reboot. So I need to restart this thing to have my pen working. And also need to restart this. That's annoying. So, okay, I get everything back almost. So yeah, sorry about that. So let's see. So for the KLT tracker, so as I said, like it's an extension of like the Lucas calendar. So last time we have basically like the main idea there is a when we have optical flow is a we are basically warping like from, in this case just shifting like from previous frame to the next frame here. So this time in this case let us simplify the symbol a little bit. We have the next frame, we will just use this as I here, we remove the index T here, and the previous frame we just call it a template, so we'll have T here. So so then I basically have the next frame. I want to have like the next frame is I, and I shifted, like let's say I shifted again like last time, shifted by some UV here. Maybe I can write it as a vector. Maybe not. Maybe shifted like this. And I want this to be like similar, right? Now let us make it even more general, as you see here. So I'm going to not just shift just individual pixel, but I do some kind of warping. So I have this function here, say it will be like more complicated warping function. So and it can be like parameterized by this parameter P here. So therefore I have this I have like warp this basically X and Y here. So this is a vector, this is a vector here. So this is basically like the new new coordinates, like new X and Y here. So I want this to be similar, right? So I have like minus TX here to be as small as possible. So therefore, like maybe we can like just minimize the sum of that over like all the location here. So basically it's like very similar to than before, but we have this V and U here. Now it's like will be modeled by some model here, let's say, and parameterized by some P here. And also we simplify the notation a little bit. So instead of like next frame, previous frame, we simply say the previous frame is like a template T here. Now this is the basic idea, like the formulation of Lucas Canada and sorry, like the KLT tracker. And let me maybe go to some I guess maybe it's still better for me to directly use the slide here. But this one again, I need to restart it again. Maybe move to here. So as I said, like, let me repeat a little bit again. So I have, oh, actually I didn't have this showing, but it's okay. I have this one again. Like I'm trying to, this is my objective basically. This is my objective here. And I'm trying to minimize this. I find the parameter P here, like to minimize this basically. And in terms of like how we model this warping, like that, you can do many stuff, right? Or everything that we learned before. For example, you can do just a shifting translation, or you can do like shifting and rotation. So a rigid kind of rigid motion kind of like rigid motion, that kind of like operation. And you can also have similarity. You can do affine and projective and so on. So this is just a illustration. Like, okay, this equation is like you don't need to bother like getting to this here. But what I'm saying is like this can be the choice here. Like you can do like for the warping, for the W there, and that's the power of this KLT tracker, you didn't really exactly specify like what kind of W here. So in general, you can be any kind of W, as long as you can model it with like some kind of parameter P. So then like, then the thing we want is basically this guy here, right? So we want to try to minimize this, again, minimize this one here. Now what we're going to do is like, we want to find the minimizing with respect to P, right? So we have P here is the parameter. So we want to find the P that actually like do the model that kind of this transform this coordinate accurately. And so for this guy to be minimized, so what we can do is let's say P0 is actually the optimum here. Let's say we have P0 is the optimum. Now if P0 is optimum, then this one should be, if we take derivative with P0 with respect to this delta P, like if we shift P0 by some delta P here, this gradient should be equal to 0 as well. This is just like you think of like if you have like in 1D case, I say if here is optimum here, if this is the optimum, you change a little bit, let's say, right? You change a little bit. This one should be equal to, basically the slope here should be equal to 0, right? So therefore, this is some standard trick people do like in optimization here. Like if you're trying to directly kind of like optimize over P, like for example, I take derivative of P here, so it will be, yeah, you can do it, but like it won't be a good approximation. Because here like you cannot write away what I want to say is like, yeah, as you will see, because like what we try to do immediately is like this one here, if I write like this, if delta P is small, then what I can do is say I can do a Taylor series expansion, right? So if I have this one is not small, I cannot do the expansion here. So now we see Taylor series expansion many times in this course here, but note that we need to be careful here. This is a little bit more complicated case because these are vectors here, right? The parameters in general can be a vector. So and what I have is basically I have something like a function I of W. W here is actually also a vector here, right? Because after warping, like, or actually maybe I should pause like for a question. Like, I say like W is a vector here, right? How many components are here for this W here? Basically the dimension of W. Oh, is my question is clear? Yes. It's a simple question, but I just want to make sure you guys say, yeah. So we have images like X, this is like 2D, so like after warping is still 3D. So now I think of like I take derivative of this guy with respect to P, right? P can be, it doesn't have to be 2D, it can be like high dimensions. But okay, before that, like we say, like we do a Taylor series expansion here. So we will expand around this P0 here. So therefore I have like I, W, X, P0, right? And then I should have like delta P times, this will be the kind of the partial derivative of, actually this will be more, actually, I probably should be precise right away. This should be like so-called this Jacobian, or whatever, like if you think of this guy here, wait a sec. Actually, this is not yet a Jacobian yet. I guess maybe I can just really do it as a gradient. So this is a gradient of I with respect to P. Okay, with respect to P, right? But I itself is a function of W, right? And function of, so then you have chain rule, right? So you have I as a W itself is a function of P, something like that, right? So I can ignore this X here. X is, in this case, X is really not a variable here because we are interested in P here, right? So we can just think of like I is a function of W and then a function of P. But W itself is a, so you see like P is a vector, W is also a vector. So I is a function of, so I want to say is like, so if I compute like gradient of P here, so it should be equal to partial derivative of I with respect to, let's say I have like, oh, okay, maybe I write it more precisely W because that's two-dimensional, right? So maybe I have W1P and W2P here, right? So then this guy will be equal to partial derivative of I with respect to W1P, right? And then I have gradient of like W1 with respect to P plus partial I partial W2 P gradient P W2. Okay, I think I write it correctly. And this thing here, if I put it like I can group that together, right? If you look at this one here, this one partial W1 P. Okay, again, like this kind of stuff, like let me slow down like step by step, like, because it's easy to show all this equation, like, but it's often like we thought like we understand that, but we actually don't because like, we don't even know the dimension. No, okay. Now in this case here, let's say I have P. I mentioned I can have like, okay. Let's make another question. Like if you can't remember. So if I have like P is a P is a, okay, let me, it may be a little bit, okay, I guess I not sure it's challenging or not. But let's say like if I have this swapping as a homography, so you remember what's homography, right? So it's the most general case. It's like something like you multiply by a matrix and so on. What is the number of parameter in this case for P? So if I say for homography, do you guys say have remember? So what I mean is like, if that's good, that's good. Yeah, that's a very good guess. That's almost correct. I will count you as correct. So yeah, you if then you have like, remember like the homography will be like, basically you have the input coordinate, then you have X will be represented as a homogeneous coordinate, something like that, multiplied by a by the homography, that is basically matrix 3 by 3. You are almost correct, but I will count you as correct basically. But know that like that's actually when you are in the homogeneous coordinate, the scaling doesn't matter. So therefore, you actually reduce the dimension by 1. So because I have, this is the matrix, I scale by S is the same matrix here, or the same transform here, or same mapping here. So therefore, like actually I only have 8 degrees of freedom, but it's okay. You guys get it like almost right. So Now, so let's say I have the number of parameters. Let's say I'm doing homography, then I have P is like 8, like, or 9, depends how you count it, like 9 parameters here. So now I can, if I look at this one here, so see, like, if you can kind of connect this equation here with the equation here. So what I'm saying, okay, I have like delta, the gradient of I with respect to P multiplied by delta P. Okay, so be this term, right? So, okay, therefore, like this guy here, actually it should be this one here. So, so you see, like I can copy it in vector form, right? So I have this one, the gradient of I can write it as a parcel I, parcel W1, parcel I, parcel W2 here. So this is basically the gradient of I transpose here. And I have this term here. So I can write it as a gradient P W1, gradient P W2 here. So as this guy. So that's the thing. Like people write it in some kind of notation, like parcel something. Like this is like typically the best we can do. But when you ask someone in detail, like what is actually the dimension of that, like someone may not even know. So then apparently they don't actually understand everything. So okay, do you know what's the dimension here? Like if I have P have dimension 8 here, what's the dimension of this guy? This is like this thing here. It's like this thing here. Oh, actually, by the way, like uh, I may have asked you guys before, but okay, before this question, let me ask you this a participation question. Like, do you guys learn gradient like here? Because I already assume that you guys know gradient. Of course, I think like we used that before also, like learn gradient in other class. Okay, yeah. Okay, so gradient, okay. So but I actually, anyway, this gradient thing is, if maybe like take a quick reminder if you someone get what's the gradient is applied to when we define gradient. One thing you need to be careful, like when we say gradient of a function, that function, like, okay, maybe I start with something like that. Like if I have, yeah, it's okay. I guess so. I won't go into that. But what I want to say is that if you talk about a function of gradient, you need to be careful that like you're actually talking about a scalar function with a vector argument. Otherwise, like you don't actually have a gradient, because like the definition is really like the gradient of something like f with an argument of x with respect to x is actually equal to the partial derivative of f x1. So let's say this is a vector argument here, x1, let's say x1, x2, x3 here. So then the gradient will be like just partial f, partial x1, partial f, partial x2, partial f, partial x3, and so on. So that will be the gradient. Now, given you this information here, get back to here. What's the dimension of this matrix here? Yes, P has a dimension of 8. So here we're still assuming, okay, P have a dimension of 8 here. So any guess? So so it have some the dimension somewhere should include 8, right? Um, so is my question clear? Like, yeah. So this one here, what's the dimension of this one here? Yeah, that's a good guess. You have 2D. Yeah, here know that here like each of this guy had actually a 8 dimension. So I have 2 pieces here, right? So therefore it's actually just 2 by 8. So like this is a this one. I mean, for example, like for the first one here is really just a parcel W1, parcel P1, parcel W2, parcel P2, and so on up to parcel W. Sorry, no parcel W2, parcel W1, parcel P2, and parcel W and parcel P8, right? So this one have 8 dimensions, 8 dimension here. And then the second also 8 dimension here. So this is actually a matrix of like this. Parcel P2, sorry, should be parcel W2, parcel P1, parcel W2, parcel P2, and so on, parcel W, parcel W2, parcel P8. So okay, like I guess that's clear with all these dimensions here. So I hope you have an idea like what this rotation actually mean now. So now with that, like we can just expand things out. This is a again like this is a 2 by 1. Oh, sorry, should be 1 by 2. And then it's a 2 by 8. And this will be like 8 by 1 here. So then add together should be scalar. Yeah, that's what we expected. Like when we multiply together should be scalar. And then so we can do the again. We can do it because delta p is supposed to be small. So if delta p is not small, then the Taylor series expansion won't be accurate, right? So we need to include a higher order term. So therefore, we started here, make this assumption like delta p is small is important. So now with this guy here, we expand this, say some algebra, like here, like we just algebra basically. So, but remember that like this thing here, like we can, let's see, this is square, I can put it 2 times, right? So I can multiply by this again. So I have like this I here coming up here, and have like this delta I here, multiplied by delta W, delta P, minus T here, right? So, well, actually, I don't need that. I'm sorry about that. So I don't need to expand this here because I really doing the gradient here, take partial derivative with delta P here. So I take the derivative. It's like the scalar case, right? If you have like, for example, like x plus 2 square, right? You take the derivative with respect to x here, or maybe here is p here, right? Then take p here. Maybe I put like ip here, let's say something. Then you have like 2ip plus 2 and take partial derivative I with respect to P, right? So therefore you have this guy is basically this term here. You have 2 here, you have this one here. So yeah, basically you take the partial derivative of this guy, the whole thing with respect to P, with respect to delta P, only this guy have delta P, right? So, and again, it will be like some scalar case, maybe I replace this with like I delta P, or like maybe A delta P plus B or something like that. So I have like A delta P plus B multiplied by like partial this with respect to delta P is just A. So therefore like this is like this thing multiplied by delta P, right? That's this A here. So I have this coming up, and then then it's like really algebra. You move terms around, Then you can group the delta P. We are interested in the delta P somehow, so we compute delta P is equal to this guy now. So and we simplify a little bit, like call this thing H. So or like I call this kind of like expression like this sum here H, and then I can like just write delta P as here. So it look a little bit ugly, but it's just a simple algebra here. So now what? I compute delta P. What should I do, by the way? So it may be like a pause to think of like, okay, we start from here, saying that like, okay, let's say this is the optimum. I have this guy. I expand that. I compute the delta P somehow, and this is equal to 0. And I approximate this thing like with Taylor series expansion, solve for delta P. So now after I solve the delta P, what should I do with the delta P here? Or like what should I do next? Yeah, what's the point? What's the point? When I find the delta P, what should we do? Like we seems like spend some time to try to find this delta P here. So now we find the delta P. What's the point? Like what is supposed to do with delta P? So okay, we start with actually I guess like this is like we assume like at the beginning like P0 is something optimum, but in reality you think of like how do I use this algorithm? I probably start with some approximation of P0. Actually most natural one, I would just like take the parameter equal to 0, so or like whatever parameter, or like if I use a homography, maybe my parameter would be like just an identity to start at the beginning. There's no warping, right? This would be my original P0 here. Now, then I try to say iterate, like, or like, I try to kind of like express my P as like this P0 plus this delta P here. And then I want to have this guy is equal to 0, right? And then as I said, we expand the Taylor series expansion here and solve for delta P. And now what? Like with the delta, think of like what we have here, like at the beginning. We say that like if we assume this P plus delta P, or like we assume that P can be expressed as a P0 plus delta P here, and we solve that, like we take the partial derivative, like solve that, we'll get something 0, or like at least I will approximately get something 0 because I have a Taylor series expansion here. It won't be completely equal to 0, it's approximately equal to 0, right? So that means that, okay, this thing is actually a good solution, right? So then what I should do is actually really, I should say like I have a new P0 that will be just equal to P0 plus delta P here. And hopefully, like if I have this new P0 here, or like I update this P0, I put into this one here, I will indeed have like this one should satisfy equal to 0 here. So it kind of makes sense, right? So if I have like this new P0, or maybe I call it this now is like P1 now. If I have this like new P1 here, I have this P1 substitute into that, hopefully this one should be equal to 0. Actually, if my identical Taylor series expansion here, I should indeed equal to 0, right? But in this case, it won't be really equal to 0 because I have some approximation here. So, but that's fine. I can do it iteratively, right? I should get closer to 0 now. So therefore, what I should do is I have this start with some P0. I solve for this delta P here as what we showed earlier. And then I will update, like say like now I call P1. I say P1 is equal to P0 plus delta P. Now I solve for this new delta P again. So my delta P should depend on this P1 here. I solve that. And I say like this is P2, and I continue to iterate that. So eventually I will get something like almost get something like a Pn, almost have like Pn plus this delta P here will, okay, anyway, this equation here will almost satisfy. So that's the idea. So we have this, go through this equation here, like it's a bit ugly, but after we find this delta P, we can just iterate it and eventually get the correct like P here. So this is just an example. Let's say if I have just doing like translation, that would be like go back to the Lucas-Canaday like algorithm, right? Because like Lucas-Canaday is really just translation. So so if I have W is with parameter P is just translation, then my parameter is just have two variables, P1 and P2, two parameters here. Then if I compute this Jacobian, like partial W with partial P would be just, actually would be like this one, actually it would be just 2 by 2, and only it's actually just an identity matrix. So then I have, remember I have this term earlier, I have this delta I transpose, like if you see it here, like this delta I transpose multiplied by this Jacobian here. By the way, Jacobian is like just a fancy name that an extension of like gradient, because if I mentioned earlier, if I do a gradient of f with respect to x, this only makes sense, or like the terminology to start with is assuming this is a scalar function. So then this will end up giving me a vector, something like that. So if I have, this is not a scalar function, but instead like it's a vector function, I have f, as I mentioned earlier, f may be like composed of f1 and f2 here. So then I can kind of like generalize this gradient to higher dimension. So if I have like this partial derivative with respect to x like this is really also known as this Jacobian. It's basically just equal to the gradient with respect to x for each of the component and pack them as a matrix. Or in this case would be something like partial f1, partial x1, partial f2, partial x2. Sorry, yeah. Partial f1, partial x2, partial f1, partial x3, and this partial f2, partial x1, partial f2, partial x2, partial f2, partial x3, blah, 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 something like that. So, okay, anyway, so I guess you probably come across this like before in some other courses, but maybe again, like maybe it's a long time ago, you can't forget. So anyway, so I have, this is a Jacobian, and I have this like delta I multiplied by this way. So I need to have this guy. And if you compute the H here, so we have the H here, say some form like this, where it's like, is this term transform multiplied by this term. So it's basically get something like this one here is, and yeah. And as a nice remark, like again, this is like the matrix come up again and again, like in computer vision, like it's like again this M matrix when we talk about the Harris corner detector. So this is basically the KLT algorithm. Yeah, as I mentioned, like, okay, yeah, okay, maybe like just this is like the repeat of the summary, the entire algorithm. So we have the delta P is computed like using this equation, right? So we start with some P to start with, like some approximate estimate of P. Then we warp that image like with this parameter P here. So then we compute this guy, then we subtract from T here, and then we should compute the gradient of I. So gradient of I is really just the gradient image there, right? So actually, yeah, I guess. Yeah, I guess it's okay. Yeah, it's okay. So I have compute this gradient image here, and then compute this Jacobian as I mentioned earlier. And then compute this product, and so on and so forth. And then I have this guy, compute this guy here, and I need to also compute the inverse of this SH here. And then compute this one, and then like, okay, finally compute delta P. So I mean like, okay, this is a nice work, and this is like date back like, I don't know, almost like 40 years ago, in the 80s. And I guess this is something interesting to talk about, because you can see like this is some nice work was there like for 20 years, and people were using that and not aware that like you can improve on that. And that's a nice paper that I'm going to talk about immediately. Okay, this is just another illustration of KLT algorithm. So it's that like we can improve this algorithm, at least in terms of performance, to reduce the number of computations here. So this seems like each time you have a loss to compute, because you start with this image warp, image right here. Each time you need to warp the image, and then each consequence step like depend on this warp image here. So therefore, like you cannot reuse some of this kind of like data here. You need to recompute everything. So, but instead, like this is a nice variation, like 20 years after the KLT algorithm. Let's say the original KLT algorithm, like remember, is like we are considering this guy, right? The basic assumption is very simple. With the image, we have like a model to warp the image and then take the difference with some temperature. The temperature is previous frame. Now, what I can do is I can split this warping. Like I have like warp into P0 and then warp, and also delta P, right? What I can think of is like, actually I can do a two-step warping, right? So I can think of like, I first warp the image, or like I should warp the coordinates, really, to warp the coordinate by P0 and then warp the coordinate by delta P. So for example, if you think of like just translation, you translate by P0 plus delta P here, you can think of your first translate by P0 and then you translate by delta P. So if we do that, so what we can see is like, okay, I actually, because this delta P is really a dummy variable, right? I mean, in the sense that I can, it's positive or negative, it doesn't matter, because if I put everything negative, it's still the same, right? So I can consider negative of delta P, it doesn't change anything, because yeah, delta P is like, really, it's like a change of the parameters in any direction there. So if you think of like an opposite direction, it's okay as well. So now if I use minus delta P, but then if I think of minus delta P, I warp like the coordinate here, or like warp the coordinate of I first by P0 and then by minus delta P, and then match with like T here. I can instead think of like, okay, I warp the image by P0, but then warp the template by delta P instead, right? So this should be approximately the same. So Okay, this is a very simple idea. So if you see from here and here, it use a couple idea here. You can concatenate this like parameter like kind of like splitting into one warping to like multiple warpings, and then like you can just flip the sign or like apply the other warp. I mean, apply like part of the warping to the template image instead of itself. But once we do that, like this is pretty nice because like now we think of that what are the parameters here is delta p here, right? So when I take the partial derivative here, of course I derive the same thing here. If I go for all the steps here, what you see is like I'm actually warping the my I should say like my variable here delta p is only on my template now, and if I take the partial derivative, like it only depends on the template, it doesn't depend on the image here. So if we assume the template is not changing too rapidly, let's say if I'm tracking something, maybe like every 10 or 5 frames or 20 frames we change the template, then it potentially can like save lots of computations because like I have this template here is actually fixed, but I have this image right, it has to vary basically every frame. So therefore, like if I need to warp this guy here, it's just you can see here like I don't warp by delta p, right? I warp by just PCO. My PCO can be stay constant for a while. So then like you can think of like maybe every 20 frames I change my PCO. But then like for this 20 frames, I don't need to change anything for this guy. So okay, this is a basic idea. If you go through the equation, you see indeed we can save quite a lot of computations. So now we want to redo whatever. I won't go into detail, but we can basically redo the same thing here. Take partial derivative of with respect to delta p. Now I take partial derivative of delta p here. So again, I can do Taylor series expansion with this guy here, but now this is not P0 plus delta P, right? So it's just like equal to delta P. So I actually have this is just the template warped by 0 here. And so, and this is this doesn't change, right? And again, like more or less the same thing as before. I have what? I have this PCO of delta P. The focus is delta P here because delta P is going to change. So, okay, anyway, I solved that. Like eventually I will solve something like, again, I'm trying to solve for delta P, right? So I solve for delta P is like this. This is my delta P. I have like my what image like with PCO minus the template. Okay, whatever. So, but okay, but you see like one thing is very nice, at least H here, know that he is like now doesn't have like PCO here. If you remember last time when we have the H here, the H is like, oh, okay, let's see, go back more maybe. Yeah, I didn't explicitly write that, but actually it will depend on the, the H here depend on PCO here, right? But for this one here, the H, it's actually like you are kind of like warping like with like just a 0 here. So we say something is constant. Okay, anyway, let's look at the entire thing again. So if I try to kind of like use this like modified KLT algorithm, so what we need to compute again, like we're supposed to compute is delta P, but now see like what do we have? Like we start with the I here, we were supposed to warp this guy, and then subtract by the template, right? Subtract by this here. Then we compute delta T here, or the gradient of T here. But the gradient of T, actually, if your template is not changing, you will only compute once. And then you compute the Jacobian of W here. At again, at the parameter P is equal to 0. So therefore, it's only compute once. And so therefore, like this guy is only compute once. So therefore, this only also compute once only. And then this only depends on this way. So therefore, again, only compute once. So then I finally do this. So then like this, all this is only compute once. So then we can really move around and make an initialization step. So this move up here as initialization steps, we don't need to compute like multiple times. And this will be like the rest of the step will yeah, we just have to recompute it. So okay, I guess I am almost time. I know it's a little bit dense here, so but I try to be quick as well for this part, like because there's also many other tracker, but I didn't really get into like the other one. So like and this one is a classic one. It's like nice to talk about. And so okay, I don't know. Like I'm like 2 minutes early, so I guess you guys have any questions? If not, maybe we just stop here today. Then next time, let's see. Okay. By the way, like I am going to put up another homework soon. I'm preparing that. It will be something related to three-dimensional reconstruction. And so it'll be something like we're going to talk about next week. So I put up, yeah, probably I will put up this homework like this weekend, but don't worry too much about that if you don't understand what it's talking about, because I will going to talk about that like next week. And potentially, let's see, what was today? Oh, I cannot use the mouse one. Okay, here. Yeah. So today is 8th, right? I probably will make it due like 3 weeks again. This probably will be the last homework. So I don't know. Like that's of course my plan is that after talking about like these camera models and a little bit of 3D stuff, then we'll talk about a little bit neural network, deep learning, and so on. Of course, if you take my deep learning class, there will be a little bit overlap. So but yeah, hopefully, yeah, I don't know, there won't be like any homework for that part. I'm not sure you guys won't be happy about that, or I will be happy about that, because yeah, if I put the homework like on deep learning instead, like because it will be like 2 weeks, probably I spend some time like that would be at least the materials I cover in the homework will be maybe will be covered like by 22nd or 27th. Maybe not a good idea. Like it will be too late. So I guess that for the last homework, like this will be a new homework. So I'm not sure like how many of you like look into like solution from the previous year. So this one will be brand new. So you probably I don't know, like, so you'll see about that. Like, hopefully it will be fun. And so the thing is, originally I'm thinking like, see if I can do a video reconstructions like using optical flow and with 2 cameras. But unfortunately, it looks like the optical flow, at least like anything available on OpenCV, is not really very accurate. If I use that for depth estimation, maybe not sufficient. So I will see about that. I will play a little bit like more like in the weekend, but what I'm going to do, like for now, at least I will give you some match data points already given. So I will load a data set there. Like then you need to fill in some of this function, like implement some of the function, so that to reconstruct those points. And you probably should guess like what is that final objects in those points. So if you do it correctly, like it's apparent like what's that object. So hopefully some fun. So okay, anyway, so I guess I spend like actually more time like chit chatting. So anyway, I will stop here unless you guys have any questions on anything. So I will see you guys next Tuesday then. So sorry again like for this technical difficulty, like I don't know, like so but I will see you guys next Tuesday.